Right, in this lesson we're going to have a quick look at some of the principles behind redox titrations as well as practicing some of the calculations that you may be presented with to do with them. Now, a redox titration method very similar to that of an acid-base titration, except that rather than reacting an acid and alkali, you'll be reacting an oxidizing agent with a reducing agent and trying to determine the concentration of one of those two. Now, uh, the as with any titration, where the end point of the titration is one where the two reactants are in stoichiometric quantities, have been added together in stoichiometric quantities, as in the exact right reacting ratio is needed for neither of them to be in excess. And in an acid-base titration, we determine the end point of the titration using an indicator to tell us when there is no longer any acid or alkali remaining. Um, in the case of redox equilibria, redox reactions being used, we have to consider this factor of how are we going to actually tell that the redox reaction is complete? How do we know that we've added the exact right quantity of oxidizing agent to reducing agent, and so we've really reached the end of the reaction completely? So we need to think a little bit about that, and we will do that to start off with. Right, okay, first problem. What if we want to carry out a redox titration to determine the concentration of an oxidizing agent? So let's just do a quick recap on oxidizing agents. Here we've got some data from an electrochemical series, again, organized so that the most positive standard electrode potentials are at the bottom. And these represent the equilibria that most favor the forward direction, which is the direction where the species become reduced themselves and therefore are oxidizing something else. So we can see here that O3 being part of the equilibrium with the most positive standard electrode potential and being a species on the left-hand side, it most wants to become reduced. It is most able to accept electrons from something else, and therefore it is the most powerful oxidizing agent. Okay, so as we go, all of our oxidizing agents are on the left hand side of the redox equilibria, and as we go down the electrochemical series, the oxidizing agents become more and more powerful. Right, if we want to determine then the concentration of ozone within a solution containing some ozone, in a redox titration, we're going to need to react it with a reducing agent. So first point, we can say reducing agent is needed. Now, in the titration, we also need to know the end point, and therefore some kind of color change, some visible sign is needed to show us when we've added the right quantity of our reducing agent. So, color change required to see end point. Now, this means that whatever reducing agent we use, its oxidized form, when it has acted as a reducing agent, when it has itself become oxidized and released electrons, its oxidized form must be a different color to its reduced form. So right, so at that point, we're looking for a reducing agent, which is going to be on the right-hand side of the equilibrium and in a equilibrium towards the top of the electrochemical series. But we're also looking for a reducing agent that has a different color to its oxidized form. So if we have a look right at the top of what we've got here, we've got thiosulfate ions. These can act as a reducing agent, and these would be converted into tetrathionate ions. Now, while thiosulfate ions are decent as a reducing agent. The tetrathionate ions and thiosulfate ions are both the same colour, and therefore this is not going to be useful on its own in terms of acting as a reducing agent for a redox titration. However, if we go one down, we can see that we have iodide ions acting as which could act as a reducing agent as well. The standard electropotential is a little bit more positive, but these should still be able to act as a reducing agent for any of the oxidizing agents below them on the electrochemical series. So I- will quite happily reduce Fe3+, Br2, IO3, IO3-, and so on and so forth. So that will work. And the I- and the I2 are different colours to each other. I2 within solution is brown, whereas I- in solution is colourless. So this looks promising in terms of a reducing agent to use within a redox titration. Now let's just have a little bit of a think though. If I were to start gradually adding I- to a solution containing ozone, what would I observe? Well, I instantly get a colour change. I would instantly go from having a colourless solution to a brown solution because the I- is instantly converted into I2. And then at the end of the reaction, all that's going to occur is that we stop making any more I2, and so it stops getting more brown. So do I have a reaction where I've got a colour change at the end point of the titration? No, I do not. In fact, the colour change stops happening at the end point, which is exactly the opposite of what we want. We want a colour change to occur only at the end point. So, can we sort this out? Could we do it a different way around? So if I had the I- in the conical flask, could I gradually add the O3 and get around the problem? No, because again, as soon as I add a little bit of O3, I'm going to build up some I2, which makes the solution go brown. And at the end of the titration, again, the only thing that's going to change is that, well, the color will stop changing. We will not get any more, the solution will not get any darker brown color. So that's not really going to be very useful in itself. Now, this is where we do a little bit of clever thinking and say, okay, well, colourless to brown is not very useful. However, if I started off as brown and then this was converted into colourless during the reaction, that would be good because initially, like everything would stay brown. You'd build up this colourless species, but that's not going to affect the colour. And then at the end point of the titration, the last bit of brown is going to disappear. And then I've got my clear colour change. So if we could actually run this in reverse, that would be great. So what do we do then? Because if we can't just run this in reverse because I2 is not a reducing agent, we can't react I2 with O3. That's not going to that is not going to work in the way that we want it to. So what we do instead is we take a large excess of I2 and react it with O3. So we use more, sorry, not an excess of I2, an excess of I-, large excess of I-, and we react it with our O3 so that all of the O3 gets used up, but there's a little bit of I- left over. And the depending on how much O3 we get a certain quantity of I2. The more O3 that was present, the more I2 we get. Okay, so the quantity of I2 generated is directly to do with the amount of oxidizing agent that we had at the beginning. So what we're doing, we're taking a large excess of I-, we add it to our oxidizing agent. The oxidizing agent oxidizes as much of the I- as it possibly can before getting used up itself, and this generates some I2. And the quantity of I2 that is there is dependent on how much of the oxidizing agent was there. Right, then what do we do? Well, we've got a quantity of I2 which reflects the quantity of the original oxidizing agent that we had. So we've now got a solution containing I2, and this can then be titrated with the thiosulfate. So the I2 is converted back to I minus, and the thiosulfate is converted into tetrathionate. And then at that point, we get the color change in the direction that we want it to. We start off with a brown solution with lots of I2 in it, and then at the end point, it will go from having the iodine color to having a colorless solution. And then if we've got a standard solution of thiosulfate, we can determine how much iodine was present. If we know how much iodine was present, we can then determine how much of the oxidizing agent was present right at the start. So we've got an indirect titration here. So rather than not titrating the oxidizing agent directly, we are titrating the iodine that is generated by the reaction of the oxidizing agent using the thiosulfate. Okay. So going on to having a look at the actual method that we'll use then. Method for determining the concentration of an oxidizing agent. Step 1. We need a known volume of the solution of the oxidizing agent to be measured out. So we need to know what the initial volume is, and that will have a certain quantity of the oxidizing agent in, which is at this point unknown. Step 2, you need to then add a similar volume of sulfuric acid to that solution of the oxidizing agent with excess potassium iodide, and everything needs to be swirled up to make sure that the oxidizing agent completely reacts with the potassium iodide, so that there is no oxidizing agent left and all of the oxidizing agent has been used to convert the I minus into I2. Into your burette, you're going to have a standard solution of known concentration of sodium thiosulfate. And then the sodium thiosulfate is going to be gradually added to the solution in your conical flask until there is only a very small amount of iodine remaining. At this point, the solution should be the color of pale straw, so kind of a very pale, slightly brownish yellow color. Now, when the quantity of iodine is so low that it's this very diluted color, obviously we're in danger of getting an imprecise endpoint because we're not going to be able to see the color very easily. But thankfully, we have an indicator which we can use to make even very small quantities of iodine visible, and that is starch solution. So we add in a little bit of starch solution, and even if there's only the tiniest trace of iodine left in the solution, you get quite a strong blue-black color. So from this point, after you've added the starch, you can add the sodium thiosulfate dropwise until the blue-black color produced by the starch with iodine, it disappears and we get a decolorized solution. Okay. And that tells us then that all of the iodine is reacted completely. Right. Having gone through that theory, let's have a look at what one of the questions on this particular type of titration might look like. So we've got quite a bit of information to read here, so let's begin by doing that. Brass is an alloy of copper and zinc, the proportions of which have varied to create a range of brasses with different properties. The percentage of copper in a small brass screw was determined as follows. The screw was weighed and its mass was found to be 2.19 grams. Some concentrated nitric acid was added to the screw. This was carried out in a fume cupboard. The copper and zinc both reacted to form soluble nitrates, as well as nitrogen dioxide and water. The solution was neutralized. It and the washings were transferred to a 250 centimeter cubed standard flask and made up to 250 centimeters cubed with distilled water. 25 centimeter cube samples were measured by pipette into conical flasks and excess solid potassium iodide was added. The zinc did not react. Copper ions reacted according to the equation as follows here. The liberated iodine was then titrated against a 0.106 mole per decimeter cube solution of sodium thiosulfate, adding starch to the indicator near the endpoint, and then we've got that equation there for the reaction between the thiosulfate and the iodine. The mean titer was 23.75 centimeters cubed. Calculate the percentage of copper in the brass screw. Now, you've got quite a long process here, and it's worthwhile at the beginning of the process to work back, figure out what your path is going to be through the question. And as with any titration, we start from the end and we work backwards. Okay, so we've got the mean titer being 23.75 centimeters cubed of sodium thiosulfate, so that will allow us to determine the number of moles of thiosulfate, which will allow us to determine the number of moles of iodine in each titer, which will allow us to determine the number of moles of copper 2+ ions within each titer before the iodide was added, and that would allow us to figure out the number of moles of copper 2+ ions in the complete sample. Remember here, we've got a 250 centimeter cubed solution that contains all of the copper, all of it, and then this is separated out into 25 centimeter cube samples, which are then used in the titration. Okay, so let's have a look at going through the calculations. So step number 1 is to determine the number of moles of sodium thiosulfate. So N of Na2S2O3 in titer equals 23.75 over 1000 multiplied by the concentration, which is 0.106. So that gives us the number of moles of sodium thiosulfate as around 0.0025175. Okay, so the next is to figure out N of I2 in titer. Now, we've got a 1:2 ratio. 2 moles of sodium thiosulfate react with 1 mole of iodine. So that's going to be 0.002517 divided by 2, which will give us let's have a look. 0.0025175 divided by 2, which gives us 1.25875 times 10 to the minus 3 moles. Okay, so this then gives us N of Cu2 plus in sample. Now, we've got a 2 to 4 mole ratio between the copper 2 plus and the iodide, but between the copper 2 plus and the iodine, it's 1 to 2. So it's important not to get tripped up over this. So we're looking at the iodine with the copper 2 plus. So it's a 1 to 2 ratio. So we need to multiply that number of moles of iodine by 2. So 1.25875 times 10 to the minus 3 times by 2, which of course takes us back to 0.002517 moles. Okay, then we're going to say N, the number of moles of copper 2 plus total. Now, this was the number of moles in a 25 centimeter cube sample, so the number of moles in the 250 centimeter cube conical flask is going to be 10 times as much because it's at the same concentration. So we're going to do 0.002517 times by 10 giving us 0.025175 mole. And therefore the mass of copper that was present in the screw is going to be the moles, 0.025175, times by the AR of copper, which is 63.5. Okay, which gives us about 1.599 grams, and therefore the percentage of copper in the screw equals 1.599 over the total mass, which is 2.19, times by 100, which gives us 73.0%. And that is your answer there. Okay, so quite a lot of steps, but again, it's worthwhile noting down what you are calculating at each step. It takes you a little bit longer, but it does keep your thinking a lot clearer. Okay, right. So moving on from determining the concentration of oxidizing agents, we may also need to determine the concentration of a reducing agent, in which case we require an oxidizing agent to do this. And we need one with a color change at the end point. Okay, now in this case, because we're requiring an oxidizing agent, we want something on the left-hand side of the redox equilibria that is towards the bottom of the electrochemical series. And it turns out that manganate ions are kind of ideal for this. You've got a color change because manganate ions themselves in solution are a very, very deep purple color, and Mn2 plus in solution is practically colorless. So let's say that we were looking to determine the concentration of tin 2 plus ions within a solution. If we were titrating with MnO4 minus, we get an anticlockwise cycle here, which tells us that we're going to have a feasible reaction. E standard cell for the reaction is going to be plus 1.52, take away 0.15, because this is reversed as it's going backwards, which gives you plus 1.37 volts, which tells you it's feasible. Now you get tin 2 to tin 4, which are both do not have a color involved, but here we get a purple color being converted into a practically colorless solution, and this is actually ideal, okay, because we want to determine how much tin 2 plus we have within our solution, how much of our reducing agent we have, and so we're gradually adding the MnO4 minus from a burette, and initially it's instantly converted into colorless Mn2 plus. You're not getting any color change because straight away the tin is reacting with it, turning it into Mn2 plus. But what happens at the end point of the reaction? At the end point of the reaction, the tin 2 runs out, and therefore there's nothing to reduce the manganate 7 anymore. You build up a tiny little bit of manganate 7, which is this really intense purple color, and therefore you know the end point because you see the color change to pink. So we use MnO4 minus as the oxidizing agent, and this gives a pale pink when in slight excess over the reducing agent. So we can say that this self-indicates. Okay, so manganate ions are what you use in a titration to determine the concentration of a reducing agent. Okay, now one thing to note, and this is kind of a slight aside here, you will note on here that we have as a reducing agent ethane dioate ions, which are this species here. So this is basically a double-ended ethanoate ion. You've got two lots of the carboxylate functional group here, and this can be easily oxidized into carbon dioxide. Now, interestingly, the reaction between ethane dioate and manganate, while it is thermodynamically feasible, we can see that it must be because of the anti-clockwise cycle here. And again, you can calculate E standard cell. That's going to be plus 1.52 minus 0.49, because this is reversed, so that's going to come to plus 0.49, which gives you E standard cell of plus 2.01. So that's very much feasible thermodynamically. The reaction, however, is kinetically inhibited because both of the reacting species are negative. It takes a lot of energy for these to actually collide with each other. And so the reaction is observed to be very slow at the start. However, once a little bit of the reaction has occurred, you get some Mn2 plus being produced, and this can actually act as a catalyst for the reaction. So the Mn2 plus actually acts as an electron carrier between the two species. So the Mn2 plus reacts with some of the ethane dioate, takes away some of the electrons from that, and then transports them to the MnO4 minus, acting as a little bit of an electron trolley, if you like, going back and forward between the two species, which being both negative can't approach each other. The Mn2 plus being positive, however, can be attracted to both of them and can transfer electrons between them. So it kind of acts as a go-between. So this essentially means then that one of the products of the reaction between manganate 7 and ethane dioate catalyzes the reaction between manganate 7 and ethane dioate. We call this an example of autocatalysis. And if you are doing a titration between MnO42- and ethane dioate, you have to be careful of this, because initially the reaction will be very, very slow, and therefore you need to make sure that you don't overshoot your endpoint. Though you could solve this, admittedly, by simply adding some Mn2 plus in solution to start off with to help even out the reaction rate so that you're not sort of thrown out by a slow initial reaction where there's no catalyst, and then possibly overshooting your endpoint because the slow reaction looks like no reaction. Okay, so have the catalyst in there from the start by introducing some Mn2 plus, not from the reaction. Right, so let's have a look at the overall method for determining the concentration of a reducing agent. So, just as before, you need to start off with a known volume of your solution of your reducing agent. You add in some dilute sulfuric acid to provide H plus ions if necessary. And you would put a standard solution of known concentration of potassium manganate 7 into a burette. Potassium manganate 7 is then gradually added to your solution containing your reducing agent, and what you should observe initially is that the deep purple colour of the manganate 7 ion disappears almost instantly as it mixes into the solution of the reducing agent. Now, as the reducing agent is used up and its concentration decreases, you will note that the decoloration of the purple manganate 7 solution takes slower and slower, and this is just, again, your concentration of your reducing agent is reducing, so the reaction takes longer. Now, when it's occurring quite slowly, you know that you're getting close to your end point. So at this point, you should transition to adding the potassium manganate 7 dropwise and continue to do so until a very, very slightly pink color permanently persists. So this is showing you that the manganate 7 ions are now in a slight excess, and therefore you've reached your endpoint. You do not need to worry about the slight excess of manganate 7 because it's such a tiny excess that it's insignificant for the overall accuracy of the titration. Manganate 7 ions are very, very deeply purple in color, so even the tiniest quantity of them in excess will give you a visible color change, so long as you're careful. Right, let's have a look at our worked example then. An experiment was carried out to determine the percentage purity of a sample of ammonium vanadate 5 NH4VO3. An impure sample of ammonium vanadate 5 with a mass of 0.150 grams was dissolved in dilute sulfuric acid. This produced a solution containing vanadate 5 ions, VO2+. Now, these are produced by the hydrolysis of the ammonium vanadate 5 in a 1-to-1 ratio. One lot of ammonium vanadate 5 produces one lot of vanadate 5 ions. Excess zinc powder was added to the solution, and this reduced the vanadate 5 to vanadium 2 ions. The solution containing vanadium 2 ions was titrated with potassium manganate 7 of concentration 0.02 moles per decimeter cubed. The manganate 7 ions oxidizes the vanadium 2 ions back to vanadate 5 ions. The volume of potassium manganate 7 required was 35.50 centimeters cubed. So what you notice here is this is not your straightforward potassium manganate 7 titration, as we do have the case where we start off with vanadate 5 in solution. We then convert that into vanadium 2 ions by reacting it with the reducing agent, and then we titrate the vanadium 2 ions. So it's got a few more steps, but the relationship between everything is relatively straightforward. 1 mole of vanadium 2 ions came from 1 mole of vanadate 5 ions, which came from 1 mole of ammonium vanadate 5. So you just need to keep this clear in your head. Number 1, the manganate 7 ions react as shown. We've got an equation here. Show by writing the appropriate half equation or otherwise that 5 moles of vanadium 2 ions react with 3 moles of manganate 7 ions. So we want to construct the half equation for the reaction of vanadium 2 back to vanadate 5 again. So we need to begin by noting the oxidation states of the vanadium in both. So we can determine that 3 electrons have been lost as the vanadium 2 is oxidized, so we can put plus 3E minus on the right hand side. Then we just need to balance up oxygens within this case. So we've got 2 oxygens on the right, so we need plus 2 lots of H2O on the left, and that introduces 4 hydrogens on the left, so we need to have plus 4H plus on the right hand side. So that's now balanced. Now we can see within this equation that 3 electrons are transferred. So we'll note down oxidation of V2 plus releases 3E minus. Therefore, 5V2 plus required to release 15E minus for the reduction of 3 3 lots of MnO4 minus, each of which requires 5 E minus. Okay, so that's that first bit sorted out. Next question. Calculate the number of moles of manganate 7 ions used in the titration. Number 2. So we've got the volume of potassium manganate 7, we've got the concentration, so this is simple enough, 35.5 over 1000 times by 0.02, which gives us 7.1 times 10 to the minus 4 moles. Okay, and number 3. Calculate the number of moles of VO2 plus in the original solution and hence the percentage purity of the sample of NH4VO3. Give your answer to 3 significant figures. So we need to apply the stoichiometry which we determined earlier on here. We know that 3 lots of manganate 7 react with 5 lots of vanadium 2. So moles of vanadium 2 plus equals 5 over 3 times by the number of moles of manganate 7, which gives us 0.00183 moles. This is going to be the same as the number of moles of vanadate 5. Which is going to be the same as the number of moles of ammonium vanadate 5. Okay, so at this point we can determine the mass of ammonium vanadate 5. We're very usefully given the MR, so we would just take the number of moles multiplied by the molar mass, which gives us a mass of 0.138 grams, and therefore the percentage purity is the mass of ammonium vanadate 5 that we know we have, 0.138, divided by the impure mass, which is 0.150, and times 100, which gives you a percentage purity of 92.2%. And that's your final answer there.